Hello, welcome to this live session. So please post your queries if you have any questions related to the material covered until now. Especially we can divide, because there will be 3 live sessions. So we can divide module 1 to 4 in this session, and then we can take 5, 6, 7, 8 in the next, and then remaining modules in the last one. Okay. Yeah, so you can post your queries and then we can discuss if I So until we get some queries, I will just briefly discuss what we have covered in the last 4 weeks. So in the module 1, which was introduction, in module 1 we discussed, we can have slides. In the module 1, what we discussed was the introduction. So we talked about what is fluid mechanics, what are different terms, fluid kinematics, statics, etc., and then how it is important for a chemical or biomedical engineer. Then we talked about some introductory concept in week 2. We also did some review of basic mathematics, especially the vector algebra and the differentiation of vectors, tensors, etc., so that when we are solving the problems, we are well aware of the vector operations. In the next module, module 2, we discuss some introductory concepts. For example, Eulerian and Lagrangian framework and related concept of system and control volume, which we are using, say, in module 5 when we are deriving the Reynolds transport theorem. And in the Reynolds transport theorem, what we do is we change from system formulation to control volume formulation. Then we discuss some of the common terminologies, for example, laminar and turbulent flows, what is boundary layer, Newtonian fluid, viscosity, etc. And in one lecture we discussed about flow visualization, for example, what are path lines, streamlines, and streak lines, and so on. Then in the third module we discussed dimensional analysis, which is the simplest but quite powerful technique in terms of getting some insight into the flow physics and understanding the dependence of a particular parameter, for example, drag force on the size of the body, on the flow velocity and fluid properties, etc. So dimensional analysis also helps us in design of experiments and reducing the number of experiments that we might need to do for a particular purpose. Then in the same module we discussed about similitude, which is that how we can look at the flow phenomena at 2 different system sizes. For example, if you want to design an aeroplane, how you can do experiments in a wind tunnel in a scaled down model and keep the flow parameters same, so that it is easier to scale things up. or from a chemical engineering perspective, when you are working with a lab scale model and then you scale up to a plant scale and then finally a pilot plant scale and then finally to the plant scale. So how this scaling up can be done? We talked about geometric similarity, we talked about kinematic similarity and dynamic similarity. Then in the fourth module we discussed about fluid statics, so pressure distribution in a pool of liquid and then forces on the submerged surfaces on a body. Okay, so these are the four modules that we have discussed till now, and in the next module, which is fifth module, we have macroscopic balances, where we first derived Reynolds transport theorem, in which we can relate, or using which we can relate the system any extensive property from system formulation to a control volume formulation, and using this we have derived mass conservation, momentum conservation and energy conservation equation for integral analysis. So using this analysis we can find the quantities or the integral quantities, such as the total force on a fluid, etc., or drag force by a flowing fluid on a body. Now there was one question in the list of questions for this live session, which simply said industry research. So while we have discussed this in the introductory lecture, I will just discuss it briefly now, that how it is useful, or how the knowledge of fluid mechanics is useful, or what are the topics then what can work on for the research which is useful to the industry. So in the process industries, if we take the example of chemical process industries, we have a number of process equipment. We have heat exchangers, we have reactors, we have distillation columns, separators, etc. And in all of these systems, the flow is in a continuous manner. So except a few industries, especially pharmaceutical industry, the flow in most of other industries is continuous. So when the flow is continuous, we need to understand the flow behavior, because when we talk about, say, heat exchanger, in most of the heat exchanger, the heat transfer is caused because of the convective heat transfer, which strongly depends on the velocity field. So if we need to understand heat transfer, we need to have the knowledge of velocity field. So if you are designing a heat exchanger, or if you want to troubleshoot a heat exchanger, or if you want to develop a control system for a heat exchanger, then we need to understand the flow behavior in this heat exchanger. Now the systems that have been developed until now, they are basically, or most of them are based on empirical equations which have been developed for a particular set of conditions. With the advancement in fluid in computing power, we can now solve the Navier-Stokes equation, which we will derive in module 6. These are the nonlinear differential equations which can be used for differential analysis, and they represent the fluid flow behavior. So those equations can be solved using computational fluid dynamics, and we can get knowledge of fluid flow, as well as from fluid flow, heat transfer, and if there is mass transfer and reactions. So we can do detailed modeling of reactors. We can try to improve, or to improve the performance of the reactors for process intensification. We can understand the flow behavior in these process equipment. So some examples are, say, bubble column reactors, stirred tank reactors, packed and fluidized bed reactors, heat exchangers. So the flow in most of these systems is multi-phase. And one of the important topic of research these days is looking at the multi-phase flow behavior, because the flow is relatively very complex in these systems, and you need to model, for example, if you have two-phase flow, you need to write down the equations for phase 1 and phase 2 and what are the boundary conditions. And the complexity further arises that you have different arrangements of flow in such multi-phase systems. So the scales involved in such systems can be several order of magnitude. For example, when you talk about, say, a bubble column reactor, in a bubble column reactor, what you have is a continuous pool of liquid, and in this liquid you introduce gas through a sparger and the gas goes up. Now gas will be in terms of bubble. Now the size of these bubble can be homogeneous, they can merge together, they can coalesce, and that will decide what kind of flow regime or what kind of gas liquid distribution you will get in your system. So all that is very much relevant for the industrial applications. Now, so all this can be done for the design of new equipment, for scaling up of a particular process, or troubleshooting an existing process. So, for example, if you have some problem or if the product is of not appropriate quality, then you can look at the flow behavior into it. You can try to see, and then if required, you might need to do the modeling or some experiments to understand that what is causing the problem. Another example, for example, for upstream petroleum engineering, where you are looking at the reservoir of oil and gas, and one need to understand that how the flow happens in a reservoir. So we need to understand flow in the porous media, because the pores are of very small size in the oil and gas reservoir. So we need to understand the macroscopic behavior as well as the microscopic flow behavior, so that we can develop, based on this microscopic behavior, we can develop models which can be used for macroscopic models. So those are some examples for process industries, and we can do modeling as well as experiments. Or the modeling can be one-dimensional simple models, so that you can do some back of the envelope calculations and find out what is happening. Or you can do some experiments and find the problems of relevance. Generally, it is the combination of modeling and experiments that you can get detailed information about a particular flow, because you might need to validate your modeling with the experimental data. At the same time, experiments cannot provide all the information. So simulations can help you, and they are also quick. So you can look at simulations and modeling together and try to see a system as a whole. Now, if we look at biomedical industries, so we just look at, for example, cardiovascular flows. In the cardiovascular flows, all the biomedical devices that are required, for example, design of artificial heart valves, or what are called prosthetic heart valves. So design of such heart valves require the understanding of the flow behavior in the heart valves, because if you have higher values of shear stress, then it may cause say platelet activation, and which can cause thrombosis and may result in problems. So designing of heart valves requires a good understanding of the fluid mechanical behavior, apart from other factors such as biocompatibility and other different factors. Similarly, design of when the left ventricle, which provides blood to peripheral organs or all the systems, then in such a system, if it is not working properly, then what is used is what is called left ventricle assist device. So it aids or it helps in increasing the pressure or pumping the blood through a ventricular assist device, or through the systemic circulation. So design of such left ventricle assist device, or what is called LVAD, is again we need to understand the flow behavior in such systems. So in the industry as of now, CFD or computational fluid dynamics as well as experiments are used to understand the flow behavior in such systems. Then patient-specific modeling is something which people are looking at increasingly, so that it can help. Patient-specific modeling is basically that the clinicians, they can get the CT images or MRI images of the diseased arteries of the patient, and then some CFD simulations can be done based on the clinical data using as boundary conditions, and one can simulate the flow behavior. Now, for example, a bypass surgery needs to be done, and the cardiologist have 2 or 3 different options at his disposal, and he need to make a decision that which one will be the best in terms of the flow. So CFD modeling or CFD models which can quickly do this will be quite helpful in such a case. Then if we talk about, say, pulmonary flows, then inhalers, we come across a number of inhalers, for example, for asthma patients. And the design of such inhalers, one such inhaler is, say, dry powder inhalers. So design of these dry powder inhalers further require that because the goal here is that the powder that is the drug that needs to be deposited in the lungs so that it can be effective, that needs to be deposited, or that needs to be transported in such a manner that maximum deposition can happen and minimum wastage of the drug is done. So for that, the design of dry powder inhalers is quite important. So these are some of the examples that I have given from process and biomedical industries. You can post questions if you have further questions. So if you have any questions, you can post. So we will close this session in 5 minutes. If you have any queries, please post it. Otherwise, we will close it in next 5 minutes. Nevertheless, you can send your questions by email, or you can post the questions, and we can take it either in the lectures or in the next live session, or I can reply them by email. So we will close the session now. Thank you. If you have any questions, you can always send an email and I can reply by email, or I can discuss in the next live session. Thank you.